Okay, let's talk about Unit 4, Topic 3, which is particulate models and diagrams. Let's get right into it. So, particulate diagram essentially is just a picture or a drawing that we use to represent a chemical equation / a chemical reaction. So, no matter if it's a chemical or physical process, we can translate it into a particulate diagram where pictures or symbols can be used to represent the equation. I don't know what that is right there. You should be able to interpret, in other words, understand what they are trying to show you, and that would be a MCQ when you never have to draw one yourself, but you should also know how to draw them when we get into free response or our FRQ section. Okay, and then when drawing, just make sure you keep these two things in mind, that you have to take account for relative particle size. So some particles are just going to be bigger than others, and we know this from atomic radius. It's funny how these periodic trends keep getting brought up. It's really crucial that we understand our periodic trends. And secondly, we have the law of conservation of matter, which says that matter basically just doesn't appear out of anywhere. This matter has to come from this previous matter in transition. So we can't just have extra stuff from when we started, and vice versa. We can't have less stuff than when we started. So let's look at this quick example. So we have H2 and O2 forming together into liquid water. Since we're going from a gaseous state to a liquid state, remember what we talked about in the last video, gases have lots of energy, they're bouncing off the walls, they're filling as much space as they can, and they're going really fast, whereas liquid water, it still has particles moving around, and that leads to why it can be poured and stuff, but it's not as energized as the gas. So we're going to see a release of heat or chemical energy that comes in heat, and we're going to have a negative delta H, which all that means is that our reaction is exothermic, and we haven't looked much about that yet. We'll see some stuff about that in a future chapter. But first, let's write the balanced chemical equation first, and then we will look at a particulate diagram of this reaction. So we have H2, and we talked about these both being gaseous, plus O2. This is also gaseous. And we only have one product in this reaction. We have some amount of H2O as a liquid. Okay, and then we have 2 hydrogens on both sides, but we only have 1 oxygen on the product and 2 on the reactant. So we're going to pop out a 2. And that changes our hydrogen count from 2 to 4 on the product side. So we're just plop a little 2 in front, and then there we go. That is our balanced chemical equation. Okay, and so secondly, we're going to look at this particulate diagram. So this is a really simplified version of what you're going to see on your AP exam. I have a more intricate one when we get to the next question. But first of all, one of our guidelines is already messed up because we don't have the relative particle size. We know that oxygen is a lot bigger than hydrogen. So if we figure out which one is which, then we can better correctly draw the molecules. So we have 2 of these black molecules and only 1 of the white molecule. So the white one is going to be our O2, which is our limiting reactant, meaning that we only have 1 of them and we have 2 hydrogens. So this is going to be our hydrogen here. And this is just showing one reaction taking place, but as we'll see in the next one, there can be lots of reactions that take place simultaneously, of course. And then this is our water. This one is easy because we only have 1 product. But that's essentially what we're going to see. So the reasons we know that this is our particulate diagram is matter is conserved. We start with 4 hydrogens and end with 4 hydrogens. We start with 2 oxygens, end with 2 oxygens. There's a correct rearrangement, so they're going into water. It's not going to be like a hydroxide and a hydronium, which would kind of disorient. That would be, some acid-base chemistry because we're giving off basic and acidic protons. And then we also have this one-way arrow, which we drew previously. We know it's not a reversible reaction, so that will also be a guideline for how we know this is our reaction. So let's look at a sample AP exam question. So the reactions or the reactants represented above are placed in a vessel and this reaction occurs. Which of the following best represents the contents of the vessel after the reaction has proceeded as completely as possible? So we need to know a few things. So we're going to have some extra stuff left over. The question kind of implies that. It's saying that it can't proceed to completion, but it can do as much as it can. So let's eliminate some distractor answers. So we have 2 carbons here, and we only have 2 carbons. So our product side has to have only 2 carbons. So we know that it's not going to be D because we have 1 carbon, 2 carbon, 3 carbon, and 4 carbons. So we know it can't be D. Secondly, we know that these carbons are not going to form bonds with each other because that's not how carbons that's not how carbons work. So we know that A is not going to be it. If you'll notice, actually, all these carbon is not a diatonic element, so we're not going to ever have a C2. We'll have some H2 and O2s, but we'll never have a C2. So we know that A, sorry, trying to get this text box away. We know that A is not going to be our correct answer. So now we're left with B and C. Well, this reaction looks like it's gone to completion because we have CO2 and H2O, but we are missing some things. If we look, we only have 1, 2, 3, 4, 5, 6. Oh my goodness. 7 and 8. Right? So we have 8 oxygens on this, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 oxygens there. So the amount of water molecules are correct, right? Because we only have 8 hydrogens, so we can only make 4 water molecules because 4 H2O is going to have these 8 hydrogens. But we are going to have an extra of O2, and that's not represented here. There's no O2 molecules just hanging out in the end. And so if we look at this, we have 2 CO2 molecules, which makes sense because we have 2 carbons. We have the 4 water molecules because we only have a maximum of 8 hydrogens, and we have these 2 extra ones, which accounts for the conservation of matter that we see in the first problem. So C is our correct answer. And that is it for particulate diagrams and representations. Let me know if you guys have any questions in the comment section below.